Okay, in this video, we're going to look a little bit more in detail at this device called an electroscope. Now, there's all kinds of electroscopes, and if you look in the electrostatics demos, you'll see that there is one that says electroscope, and you can see exactly. You really want to watch that video. In fact, you can watch it in combination with this video, and you'll see all the things I'm about to talk to you about right here. I demonstrated with an actual electroscope, so you can see those things working. Essentially, an electroscope is just a device that it's a metal object that is capable of accepting charge. Charge can be passed on to it very easily. However, it has two parts to it, and the important part of it is it has leaves. So one way you could make it is you could just take a piece of aluminum foil and kind of fold it over and just let the aluminum foil kind of dangle down. Now, if you were to pass charge onto the aluminum foil, because the two sides would have the same charge, they would start to spread apart from each other, and that would indicate to you that you have charge. The more the leaves spread apart, the more charge you're going to have. So the electroscope that you'll see in almost every book is going to show that type of electroscope. It's a very, very thin piece of aluminum foil or some other kind of metal foil. And as you charge it, the leaves will push apart. And when you discharge the charge on the leaves will come back together. Now, I'm still going to use that term leaves, even though the electroscope that I prefer to use, I don't know if I would really call it leaves. They don't quite look like leaves. They're not necessarily flat. All flat, but they work on the same principle, and that is that as the charge develops on the electroscope, the leaves begin to move apart. The more they move apart, the more charge that you've placed on the electroscope. So it's a way of telling approximately, in a relative sense, how strong is the charge on this thing, and then also it's a way of telling what kind of charge. Is it a positive charge or is it a negative charge? So again, you can see the video just shows exactly what the electroscope looks like if you want to see the actual electroscope in person. But ultimately, it's a device that looks something like this. We're going to start with a neutral electroscope. So this would be a large plate. It might be square or circular. We're looking at it from the side. But if I were to look at it from the top up here, I would see that it's usually round or sometimes it's square, but most of the time it's round. That is connected, that's metal. Okay, that is connected to another strip of metal that goes down, moves over like this, and then drops down like this. So this is one long continuous piece of metal. It's like a flat strip of metal. Sitting in here, would be a small hole punched through here, and inside here would be the leaves. Okay, so I'm going to draw that to make sure that's clear. These are the leaves. These are what will reveal the charge. And right now, at this point, obviously this object is neutral because I have not drawn any charges on it. That's how I indicate that things are neutral. So let's see what happens when we move a charged object close by to this. We're going to see this thing that we've been talking about a lot in this class, polarization. I'm not going to charge it yet. But what I'm going to do is bring something close to it, and the electroscope is going to have a very dramatic reaction. And you can see that in the video, and you may have actually even seen it in class. So in this first case, in order to get this guy polarized, I'm going to bring in it doesn't really matter what we bring in, but in this case, I'm going to bring in a negatively charged rod. So we use plastic rods for a lot of our electrostatics labs. Okay, so I've brought something that is very strongly negatively charged. It's producing a large electric field around it. These guys, the electrons inside, this is all metal. Okay, all metal. The electroscope is all metal on the inside so that the charge can move around easily. The free electrons will respond to this. Now, the protons, unfortunately, can't really do anything because, again, in a metal, the protons are locked in place. They're in the nucleus. They can't really go anywhere. They can vibrate, but they don't really leave. But the free electrons can leave. So what is ultimately going to happen is that they are going to push away, and I'm going to draw 6 charges up here. So 6 up here. I'm going to draw 6 on the bottom. These are all positives. Okay? Now, why is this positive charge here? Because some of the electrons have left. And where did they go? They went farther away. They want to get away from this charge right here. So what will happen is I'm going to draw 3 here, 2, 3, 1, 2, 3. That leaves 6 charges unaccounted for because remember, this is still uncharged. This is a neutral object. I have not touched anything that was charged to it, so it cannot be charged yet. So I have 12 positive charges on the top here. I've got 6 on the bottom. The reason why you don't see the other ones is because they are on the leaves. So because the leaves are connected to this long strip by a metal pin, they will also allow charge to move onto them. And you can see that because these are both negatively charged, they repel each other. That's what pushes them away. And then the same thing is happening down here. These two are charged, and so they want to push away from each other. And it's that repulsion that reveals that there is charge on the electroscope. Now, the thing about it is, though, there's charge down here, and there's charge up here. But if you look at the total charge, it's still neutral. It is not a charged object yet. Okay, so that is a great example of polarization. And the electroscope will show you that it appears to be charged, and it appears to be charged because of the fact that it has become polarized. So let's start with that position. We're going to bring the charged rod in close. We haven't done anything with it yet. It's polarized the electroscope. The electroscope seems like it's charged, but it's not really charged yet until we actually touch the electroscope with this charged rod. So let's come down here. We're going to draw an arrow like this. And actually, let's draw this. So the term is polarized. And it is polarized because it is positive on this end and negative on this end. So, you know, before the electroscope didn't have any special orientation or anything like that because everything was just neutral everywhere. But now it does. One end is highly positive and the other end is highly negative. Okay, but it's super important. It is still neutral. Okay, I have not charged it yet. Really important thing to understand. And what's ultimately happening is that there is a force here, a repulsive force, which will always happen whenever charge is forced down here. There will always be some repulsive force, and that repulsive force is what we're looking for. That's what's going to reveal that there's charge on the electroscope. So let's move down and let's look at what happens. I'm going to start from this picture, and all I'm going to do is I'm going to take that rod and I'm going to reach down and touch it to the electroscope. So let's draw the electroscope first. Okay, so what we're going to do is we're going to bring the rod down and touch it. Okay, and I'm not drawing any charge here because this charge is going to move on to the electroscope. Okay, so let's assume, for argument's sake, that when we do this, that we end up, what's going to end up happening is some of these negative charges are going to move on to the electroscope because they want to neutralize. They're attracted. They want to go to these positive charges. So in this case, what's going to ultimately happen is some of the charges are going to go away. So I'm going to take off, of the charges that were originally there, I'm going to take off a few of them. So let's take off 2, 3, 4, 5, 6. I'm going to have 6 positives. Now, what happened to the other positives? They've been neutralized. So an electron came down, joined with that atom, and now that atom is no longer charged anymore. Now, where is the remainder of the charges? Remember, the guys down here, they're not going to be affected because they don't want to get anywhere near these negatives, right? They're being forced to stay down here. Okay, sorry. So here's the picture that you want to draw. We've deposited some of the charge by conduction onto the electroscope. Some of the charges have now been neutralized. Okay, the charges that have been neutralized, there's still some positive charge up here, but because these have been neutralized, there's less charge up here now than there was before. So this object is now officially charged. If you count up the number of charges, you will see that there are 12 negative charges and there are only 6 positive charges. So this now has, in theory, a +6 charge, essentially. Okay, now when we pull the rod away, what's going to happen is, because these guys don't like to be near each other, and the only reason why they were collecting down here is because they wanted to get away from the charged rod, so when I pull that rod away, now they will go back and start to spread out all throughout the electroscope. Let's draw the electroscope again. So now we're going over to this picture. And everything will look more or less the same. There will be one little difference, though, and that is that the electroscope will not appear to be quite as charged. And the reason for that is, let's just count up how many charges we have to work with, right? You have the 12 down here and the 6 positives up here. That means you have 6 negative charges that remain on the electroscope. So we could draw them nice and evenly distributed, something like this. Okay, so there's the 6 electrons. They've all spread out. These guys still repel, but notice not as much as they did before, right? Because before there were 12 charges down here, so very strong repulsion. Now there's only 4 charges left down here because 6 of the negative charges were neutralized when they moved up and rejoined with these positives, leaving only 6, a net charge of 6, -6 on the electroscope. So the electroscope is now charged. But one thing you'll notice is when you pull the rod back, the leaves will relax a little bit. Okay, they'll still be charged, but they will relax just a little bit. Okay, and we would say that the electroscope has been charged by conduction, and it is officially charged at this point. Okay, that's pretty straightforward stuff, but very, very important to understand at the microscopic level what's going on. You know, this particular idea of talking about the electroscope is mostly going to be level 3 and level 4 kind of questions, where you really have to think carefully about how things move and why they move in the way that they do. But let's take a look at another form of charging that we've already talked about before. We've talked about this idea of charging by induction. That means charging indirectly. And the electroscope is a great way to demonstrate that concept of charging by induction, or by indirectly charging the object. So let's draw the electroscope to start with. And I'm going to add one thing to this electroscope that I did not have in the previous pictures. I'm about to draw 4 pictures of electroscopes. So there'll be 1, 2, 3, and 4. So if you want to make sure that you have enough space for that. We have initially a neutral electroscope. Okay, but here's one thing that we're going to add a little bit differently. In order for charging by induction to work, you must have 2 objects connected to each other. Now, in the first video where we talked about charging by induction, we looked at pith balls. Now, if you put 2 pith balls next to each other, you bring in a charged object, they will become polarized, and when you separate them, you'll trap those charges on the 2 pith balls. We're going to do the exact same thing here, except that instead of connecting this to a pith ball, we're going to connect this guy to the earth. Okay, that little symbol right there means the ground, means that you have connected this thing to the ground. Okay, it's connected to the earth. That process is called grounding. Okay, now in England, they refer to that as earthing. It's the same thing though. You know, the ground is obviously the earth. And so when you connect it to the ground, what you're basically allowing the charges to do is to go to the earth, and the earth is huge. And of course, if you, let's say, for example, you have negative charges, they don't want to be near each other. They hate being near each other. So by connecting this to the ground, they have a place where they can go and spread out a little bit more. They like to get away from each other. They don't like to be next to other negative charges. And so that's what's connecting. These are the 2 objects, the earth and the electroscope. So now in the second step, what we're going to do is same thing we did in that previous charging, and that is that we will bring in a charged rod. We'll use the same one that we used in the last one, so negatively charged. Okay, so we brought in a negatively charged rod. Now, of course, this is going to cause polarization, but just think about this for a second. So you have all these electrons up here that don't want to be near this guy. Okay, but you've now given them 2 options. One option is they go down and they have a little bit of space down here, but not very much, right? I mean, there's really not very much place for them to go. I mean, this electroscope is clearly much, much smaller than the Earth. So where do the negatives go? So when I charge this guy, we're going to put 1, 2, 3, 4, 5, 6 on the top up here, and 1, 2, 3, 4 on the bottom. So let's assume that we now have a plus 10 charge up on here. Where did those electrons go? Where did those negative 10 go? They don't go this way because there's not very much space down here. And if they have a choice between a large object or a small, they're always going to choose the large object because they want to spread out from each other. So all the negatives, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, electrons will leave and they will go down to the earth. Okay, and they will stay there unless you pull the rod away. Now, if you pull the rod away, those electrons will travel right back up the ground wire and they'll go right back and neutralize this thing, and you'll never even see the electroscope react. If I pull the charged rod away, everything goes back to being neutral exactly as it was before. Okay, but that's not what we're going to do. Okay, so in order for charging by induction to work, what you have to do is break this connection first. Break that connection so you have therefore trapped those electrons on the earth, and now the electroscope is officially charged. Now, funny thing about the electroscope is, at this point, and if you watch in the video, you'll notice that when I bring the charged rod down, it doesn't do the same thing. You know, previously we looked at it and we saw a big reaction, very strong reaction from the electroscope because of the polarization. But now I bring that charged rod down, and while it's connected to the earth, either by a wire or maybe I'm just holding on to it, nothing seems to be happening, even though the electroscope is actually charged. It is officially charged at this point. It has a positive 10 charge. But because the charge is all being held up to the top of the electroscope, nothing seems to be happening down in the lower portion of the electroscope. So as we move down to the third picture we're going to draw, this is really important to leave the And we're going to, here we go. This is like that. All right, now here's a really important thing. Oh, I'm sorry. You can't see what I'm drawing. I've drawn the negative rod is still there. Here's the electroscope. It still has all of its positive charge up here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. So 10 charges total. Here's the ground wire, but I'm going to break that connection. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 negative charges down there. Okay, now that I've broken the connection, you will still not see anything happen with the electroscope yet, but now that I've broken the connection, now I can go ahead and pull that rod away, and when I pull that rod away, you're going to see that there will be a dramatic reaction. All right, so at this point now, the ground wire has been broken, so it's no longer connected to the earth. Those charges are no longer being held up here. They really like being next to the negative charges. So as long as I leave the rod there, those positives are going to stay right there. But when I pull the rod away, what's going to happen is all these positives are going to begin to spread out, and I'm going to end up with a charged electroscope. So in this case, let's say, for example, so we have 10 charges right there. So we'll say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The charges are going to spread all throughout the electroscope, and the electroscope will suddenly, when you pull the rod away, the needle will jump. And what's different about it is that if I were to bring that negative rod back, the electroscope leaves would return back because all these positives would be drawn up to the plate at the top. Now, what would happen if I brought a positively charged rod down here? Well, if I bring a positively charged rod, these positives up here at the top will get pushed back down to the bottom of the electroscope, and the leaves will be even more dramatic. That's the exact opposite of what would have happened in this example where we charged by conduction. I actually put the negatives onto it. But in this case, I never actually touched the rod. I never touched the negative rod to this, and obviously I didn't because I got the opposite charge. I can't make something positively charged with a negative rod by conduction because conduction would always pass on the same charge. So this is a really important tool that was used by Coulomb as a way of getting both positive and negative charge and allowing him to have some sense of how much charge that he had on the thing because it gives you a controlled way. You know, when I touch this thing to the electroscope, I don't really have much control. I mean, whatever charge is there is going to move on there, but it's not like I can see it. So I don't really have the kind of control that I have when I use charging by induction. And many of the experiments, much of the work that was done by Coulomb was using this process of charging by induction. Now, just to make sure it's clear, you can talk about the positives moving around, and that'll get you up to level 3, but if you really want to get to level 4, your explanation of what happened right here between these two steps is that what really happened was that electrons that were down here were attracted to these guys, and they were always attracted. I mean, the electrons down here were always attracted, but they wouldn't move up there because the rod was there. Once the rod is pulled away, now electrons will begin to migrate up to there to neutralize some of the positive charge up here, leaving positive charge down here, and therefore there'll be positive charge all throughout the electroscope.